Hello. Thank you. Sorry about that. Can everyone hear me now? Everyone can hear me? Cool. Okay, so um, the uh, so I was saying, just making a couple of little announcements. There are plenty of slots left for the oral exam. If you just go to the calendar, you can make an appointment. The detailed instructions are linked in that announcement I made, the most recent announcement. You can see the detailed instructions. A few people have already signed up. That's good. If you're still not sure if you're taking the oral exam, that's fine. If you want to like kind of see what your grades are, um, that's fine. Just note that the grades, you might not have all of the grades available before Friday, so you're gonna want to use the what if scores like I was showing you yesterday at the end of lecture, um, to kind of estimate what your grade will be and then make your decision based off of that, because I think that's going to be the best way to do it. Because if you wait until those grades come out, you might miss your chance for the oral exam. So just keep that in mind. Yeah, I think besides that, the other thing is the online homework. Yeah, so someone's asking specifically if the grade for the quiz and the worksheets this week will be available before Friday. So that my hope is that yes, it will be available before Friday. But Matt and I have to grade those. I'm happy. I'll help Matt grade the quizzes this week, so hopefully it goes a little more quickly. But he has other classes that he's a TA for, and we both have other things going on, so we might not. My priority is also to finish writing the exam for you. So there's a lot of other things, other moving parts. So um, if all goes well, then yes, they will be available. But there might be some hiccups. Hopefully, at least one of them will be available by then. And the participation should be available by later in the day on Thursday, hopefully. So that at least is kind of small things in the grade. The other thing is WebAssign. WebAssign can't be available until Saturday because the due date is Friday at midnight, and so we can't. I can't move. I can't sync or put those grades in until the period has closed, and so that one you're going to have to estimate. I've checked the scores this morning. It looks like people are working on it. The averages are kind of going up. There's still some people who are on the bottom half, who have less than half of it done. But that's at this point, it's just kind of work on it when you can, get as much done, and then it'll just help boost it'll help boost your grade, and two, it'll help give you practice on different types of problems, and we can kind of go back and talk about topics. And it's one of the things we can talk about here, because if you looked at the calendar, or if you remember yesterday, I said these last 2 days of lecture are going to be review days. But what I mean by that is that we're going to come here, and and I'm going to kind of answer questions, so we can go back to as far as any of the old homework, any of the old quizzes, anything you've been studying that is giving you some trouble. We can talk about that. If you just want to use this chance, like if you're behind on the homework, if you just want to use this chance to open up WebAssign and work on it, and every time you have a question, you say, "Hey, how does this problem work?" You can have your homework open, and we can do that. So I would strongly encourage you to have WebAssign open at this point, and old quizzes and stuff, and bring those questions with me. I asked those of you who were here yesterday, I asked you to bring some questions for today. So hopefully you did that. And then if not, you definitely bring some tomorrow, and we'll try to get as many questions answered as possible. This is how learning works. It kind of works, and you kind of have these passes. So the first pass is when we're in lecture and I'm kind of writing stuff down, definitions, doing some small examples. But we all know that first pass isn't enough to learn something, right? Just because you were here on lecture doesn't mean that you necessarily really learned it. Okay, the second pass comes when you try the homework, or when you work on the worksheet, or when you take the quiz. And sometimes even that's still not enough. Maybe if there's a little topic you missed, or a certain type of problem that didn't come up on the quiz or the worksheet. This is now our chance to just try to put on that final coat, okay, to make sure that we really have got it, everything's really sinking in, okay, to make sure we've got everything really sunk in. So if there's anything at all, this is going to be our chance to talk about it. Okay, so let's open up the floor. Already got some coming in. Yeah, let me pull up. I have the homework pulled up here. So someone's asking about in 3.4, section 3.4, number 8, how to use Lagrange multipliers for that. So okay, cool. So see, am I going to use okay, so I'm going to use some, I'm going to take a screenshot of this and copy paste it. Okay, so oops. Sorry, messing things up. Okay, there you go. Okay, so let's start with this. This is from 3.4 WebAssign. I guess I should say that. WebAssign 3.4 number 8. Using Lagrange multipliers to find the distance between this point and the plane. Now there's a formula for the distance from a point to a plane, but we don't want to use that. We want to specifically use Lagrange multipliers. So the trick here is that we're going to use this plane as our constraint, right? So the equation for the plane, this is going to be our constraint. Come on. This is our constraint. But the question is, what's the function we're trying to minimize? Well, we're trying to minimize, right? The distance between a point and a plane, right? So if we have a plane and a point, right? You can find the distance between any 2 points, right? We have that formula. So like if I had a point over here, I can find this distance relatively easily and this distance relatively easy. But the point of the distance from a point to a plane is that there's one point on this plane which is of minimal distance, right? And in particular, it meets at a right angle. So that's how we cooked up that formula that we have back from chapter 1. But in this case, there's a point where the distance from this point to this point is going to be minimal, okay? So what we do is we say, okay, how do we compute the distance from a point XYZ? So the distance from XYZ to 3, 0, -1, right? Again, your numbers might be different. If you haven't noticed by now, some people in my office hours, we've already talked about this, but anything in red, those numbers are the numbers that change. So if you and your buddy are working on the homework together and their numbers are different, the red ones are the ones that can change. Anything in black won't change. So the distance from here to here, that's going to be the function that we're talking about. So f of x, y, z. Well, we know what the distance formula is. It's the square root of x minus 3 squared plus y minus 0 squared plus z plus 1 squared. Okay. So this is the function we try to minimize here. So minimize this. Okay. Okay. Now there's a little shortcut you can take in this problem. It's kind of cheating, but it works in this case. So what you can realize is that if you want to minimize this, right, you can ignore the square root. Or minimize this. So come up with this other function. Maybe I'll call this one h, and then the function that we actually want to minimize, right? Because if you've minimized this function, then you minimized the square root, right? If you minimize something, if you minimize a certain number, and then you take the square root, then you've minimized the square root of that number, right? Or I should say function, right? Because if you have a small, if basically because if you compare two numbers like a less than b implies, or I guess if and only if the square root of a is less than the square root of b. Because of this, then the definition of a minimum, the minimum of this happens at the same place as the minimum of this. Now the minimum values will be different, but since we're we just have to remember that whatever we find from this, we can plug in up here. Okay, this just makes the calculus easier, right? Because when we take the derivative of this is less nice because you have a square root. So I'm just going to use this one here. Just remember that the solutions we get for x, y, z, we have to plug back in here. So because since we're looking for the distance itself, right, then we're looking for the minimum value. Okay, because we're looking for the actual distance itself, not where which point is minimal distance from. So either of these will give us the point of minimal distance, but only h will give us the actual, sorry, did I say that right? Either of these will give us the point that is of minimal distance, and but only h will actually give us that distance back. Okay, and so we'll use f for all of the calculus parts, and then when we go to plug back in to find the minimum value, we'll actually plug into h. Okay, so then we just do the gradient of f. So that's going to be 2 times x minus 3 plus 2y plus 2 times z plus 1. Can simplify this, 2x plus 2y plus 2z minus 2, or no, minus 1. So, oh, nope. So that's minus 6 plus 2, so minus 4. There it is. Okay. Oh, sorry, that was a mistake. Ooh, it's too early for this. Okay. So I shouldn't be adding those together. I don't know what I'm doing. Gradient is a vector. There should be commas there, not plus signs. That's more like it. There you go. Ooh, take a sip of coffee. Okay. Now let's take the gradient of our constraining function. So in this case, that's g. That's going to be 4, comma 3, or negative 3, comma 8. Okay. 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 So then when we're going to set up a system of equations using this. So we get 2x minus 6 equals 4 lambda, right? 2y equals negative 3 lambda. And then we get 2z plus 2 equals 8 lambda. And then always remember, you know, I often forget this when I'm doing these problems. you have an extra equation, right? Because technically there's too many unknowns here you can't solve. But there is this extra equation up here. The constraint itself is an extra part of this equation. So 4x minus 3y plus 8z plus 1 equals 0. Okay. Now this one's actually pretty nice. This one doesn't require anything too tricky. It doesn't like, or if you remember some of the ones we did in class, like we're actually like, you actually had to do some weird tricks, like you had to do a thing like where you multiply this one by x, this one by y, and this one by z. You saw one that I tried to do and I wasn't able, I hadn't planned it correctly and wasn't able to do it. But this one's not going to be too bad because each of these only has one variable and besides lambda. So it has the lambda and an x, lambda and y, lambda and z. And this one has just x, y, z and no lambdas. So what we're going to do is I'm going to get a little more organized here. So I'm going to move this out of my way. Move this over here. Because, and I'm probably going to need more space here, but this equation here tells us that if you solve for x, you get 2 lambda plus 3. So I moved this 6 over, then divided everything by 2. Solve this for y, you just get negative 3 over 2 lambda, or negative 3 over 2 times lambda. Solve this for z, and you get 4 lambda plus 1, or minus 1. Okay, you can check my arithmetic there. Okay. So now you have x, y, and z in terms of lambda. We've seen that in some cases, we don't always necessarily need to find an exact value for lambda. Sometimes it just helps us see, hey, look, in this case, the lambda is just like a placeholder to see that x equals y or something like that. And then you use that to proceed in the problem. But in this case, we're actually going to need to solve for lambda because what we can do here is plug in these 3 values of x, y, and z into this equation. So let's do that here. So let me take this. So we have 4 times this value of x, 2 lambda plus 3, minus 3 times negative 3 over 2 lambda, plus 8 times 4 lambda minus 1, plus 1 equals 0. Now this is an equation in one variable, right? Just like a linear equation in one variable. You can give this to your younger sibling who's learning about equations in one variable, and they can hopefully figure that out. But if not, you just work it out yourself. So this is 32 lambda minus 8, and all this plus 1 is equal to 0. Simplifying some of these constants, we get a positive 5. So move that over, we get negative 5. Okay. Combine everything we see here. So combining the lambda term, so lambda is, so that's 40 lambda plus 9 over 2, so 89 over 2 lambda. So then we get lambda is equal to negative 10 over 89. Okay. But ultimately what we care about is the point xyz. So you get x equals 2 times negative 10 over 89 plus 3. Y equals negative 3 over 2 times negative 10 over 89. Z equals negative 4 times negative 10 over 89 minus 1. Now I will say that I did a lot of like the combining stuff here. I kind of glossed over, so there's a good chance that there's arithmetic mistakes somewhere in this. So the other thing about, I think one of the harder parts of Lagrange multipliers is that there's first of all, solving the system of equations isn't always obvious how to do, and there's more than one way to do it. But also there's so many steps that it leaves a lot of room for um, for error. Okay, but now regardless, right? This is the point. These XYZ give you the coordinates of this point here, which minimizes distance, but you want the distance itself. And so you're going to take this point and plug into H. Okay. And that's going to give you the minimal distance. Okay. Any questions on this problem? Ooh. Yeah, so even if your numbers are different on this one, the whole process is going to be very similar, right? Just your numbers will look different down here. Okay, cool. You have more questions? That's a good one. That was a good question. I figured something like that would come up. Again, I'm happy to go back as far as you want, you know. Yeah, so someone's going back to section 1.4. That's awesome. That's one of the reasons I decided to leave the homework open all quarters, because I knew I'd have these reviews at the end, and we can go back and make sure that we're all on the same page. Cool. So going back to 1.4, going way back to spherical and cylindrical coordinates. So 2, 3, and 5 part B. Okay. So let's see. So try to get as much of this as I can. So for this problem, for number 2, we're describing geometric meaning of different maps. And these are multiple choice, so that's nice. Okay. So in this case, what we're doing is we're looking at a map, analyzing it, and seeing, okay, which of these is it actually doing? Okay. So in this case, what you should be picturing is, so you have your coordinate system. This is your x-axis, your y-axis, and your z-axis. And if you have a point, right, so you have your x, your y, and your z. So if this is your point x, or I guess r theta z, and you map that point to r theta negative z, well, then the r and the theta stay the same. So this distance and this angle stay the same. And you just go, instead of up to z, you go down to negative z. So anything that was up here gets moved down here. Anything that's on this plane, the xy plane, stays where it is because the z coordinate is just 0. And then anything that was already negative, when you throw that extra negative sign, becomes positive, right? So anything up here goes down here, anything down here goes up here. And it's not like rotating. It's like it's actually just reflecting like this. So it's not the rotations. Can you see that? Yeah, I'll go a little darker. It's not the rotations, definitely one of these reflections, and we're reflecting across this plane right here, which is the xy plane. So it's this one right here. So not this one, not this one. It's going to be this one. Okay, because it's a reflection, it's across the xy plane. So everyone's going to approach these a little differently. If you kind of have a good bearing for how these coordinate systems work, then you can maybe just kind of picture it in your head. But it might help to draw some pictures if you're not super, if you're like not comfortable picturing things in your head. Okay. Okay, cool. So now let's draw a picture for this one. So you have your z, x, y. So you have r theta z and an r pi negative z. I said r theta plus pi and then negative z. So let's start again with the point like this. So you have r theta and z. So I should be doing this in blue. So this here is your r theta z. And now the point it gets mapped to, the r stays the same, but the theta, you add pi to it. So if you remember what happens to an angle when you add pi to it, so if you have, let's just look at the xy plane for a second. On the xy plane, if this is theta, where's theta plus pi? It's like right here, because that distance is pi. Pi is right 180. And so you just add 180 to it, then it's kind of going in the opposite direction. So what this is doing is it's sending this point, it's going now out here into the back. So this angle here is pi. It's kind of hard to draw, and then also instead of going up, it's going straight down. So this point ends up down here. This is r theta plus pi negative z. So anything on the xy axis, or sorry, on the xy plane, it's just acting like this rotation right here, because z, nothing's happening to z. On the z axis, it's just acting like it's just reflecting things down here. And so this is definitely going to be some kind of reflection. Let's see. Well, I mean, that was clear because of the choices here. So this one, it actually broke it up into two parts. So it's actually nothing crazy. You can, if you remember, you don't have to describe this all as one move. You can just see that this is it's a reflection with a rotation. And so we can just break it down into the two parts. In this case, you can start noticing some patterns. So negative z is sending z to negative z is just a reflection across the xy plane. So it's going to be one of these two, either, so it's going to be either this one or this one. These two talk about reflection across the xy plane. So it's not this one, this one, this one, a little bit of process of elimination. And then we're rotating. So they put a little something tricky here, but they said rotation by pi or by negative pi. Now, rotation by pi and rotation by negative pi are the same, right? Because if I subtracted pi from this, then I'd end up over here, right? I'd just be coming at it from the other angle. So geometrically, rotation by pi and rotation by negative pi are the same. What you should actually be looking at is the axis that you're spinning around. In this case, we're spinning like this. We're spinning on the xy plane. And so we're spinning around the z-axis. So about the z-axis is the fancy way to say it. So you get this one here. Okay. Cool. Now let's do part C for number 2. Okay. Okay. So this one has a little bit more going on. So this one, the Z is staying the same. So let's see. Let's draw some stuff out. Okay, X, your Y, and your Z. Okay, so again, we start with a point r theta phi or r theta z. So this here is r theta z. Now z we're going to keep the same. R is going to become negative. So that goes now back here. Right, so this radius was here. Now the radius is back here. And theta we subtract pi over 4. Pi over 4 is a 45-degree angle. So now we kind of end up over here. So this is pi over 4. We subtracted, so we went clockwise. And then we went back here. So straight up, that is r theta minus negative r theta minus 4 minus pi over 4 and z. Okay, now notice some of these just have a rotation, or just some of these just have a rotation. So the trick is noticing that there's a subtlety here, that r theta z mapping to negative r theta z, right? This point here, negative r theta z, if we imagine that r is always positive, then this gives us now a negative r. But if you remember from polar coordinates, if I have theta here, and then r is negative, so this is negative, right? Then my point is out here. But I could have just taken the theta and subtracted pi, so that negative pi. You could have also added pi, but we'll say it as negative pi. So this is the same as r theta. So these two are equal. These are the same map. Minus pi z. So making the radius, making r negative is the same as rotating by pi. Okay. So and all of this is happening about the z-axis. So then if we're rotating by pi, notice that a negative r thing is just the same as rotating by negative pi. Okay, so now let's move on to number 3. Same thing, but now we're in spherical coordinates. Oh, this one looks like I've already done before. So, well, you're going to see the answer straight away. So, maybe I'll just copy the question first. So number 3, I guess I never wrote down the problem here. So this is Webassign. Oh. Hello now. Is that better? Yeah. Okay. Yeah, my computer just like auto adjusted and turned it down real low. So this was WebAssign number 3. I guess 1.4 number 3. No, this was number 2. And then now I'm going to start WebAssign 1.4 number 3. So this one looks like I've already done it, so I won't share the options because that'll spoil it. But start with this map here. So this map we can do without necessarily drawing anything, because right, it's just taking on the theta part, we're just adding pi, which is something we've seen before. We saw subtracting pi. We saw it. Remember, the job of theta in cylindrical and in spherical coordinates are the same, right? So this adding pi here is the same as adding pi to this theta. Theta is the same across the two types of coordinate systems. So in this is just a rotation by pi around z-axis. Okay. Okay. Now B. So this one's a little weirder because you're now affecting phi, and phi is always a little more challenging. So what I'm going to do is, what I find helpful is to just look, if you imagine in spherical coordinates, right? To just focus in on the phi part of it, you just draw the z-axis. This is your z-axis. And then this is your xy plane. It's kind of weird to think about, but this line represents your xy plane. Right? You're just looking at the cross section wherever theta is, basically. And so what phi represents is basically this angle right here. This is phi, right? So I usually draw it in like 3D space, but this is how I visualize it. Usually I like put myself right, like I, put myself parallel to the plane where this angle is happening. Makes life easier. Okay. So since phi is the only thing affected here, that's the only part I'm drawing. If we send phi to pi minus phi, remember that phi goes from 0 to pi because it goes either straight up, and then you can go all the way down to, or straight down, which is pi. And so it's measuring this angle here. So if I do pi minus phi, then pi is straight down. So I do minus phi, and that puts me right here. So this here is, you do pi and then minus phi. So this is pi minus phi. Okay. Okay. So if something was above the x-axis, xy plane, it now moves to below the xy plane. So if we look at our options, that is just reflection across the xy plane. Okay. Cool. Last but not least, we have part C here. Okay. Okay. Okay, so for this one, there's two things going on. Phi is unaffected, but we're just changing remember, the rho is the distance from the origin. So we are scaling. So this is, I should use color. So this here is scale. I think it uses the phrase radial distance or something like that, radial expansion. Distance by 2. And then this over here tells us to rotate by pi over 2. around the z-axis. So theta, remember, is just rotating around the z-axis. Okay. Okay. Yeah. And it describes it as a radial expansion by a factor of 2. That scaling by factor of scaling radial distance by 2. It says radial expansion. Just another phrasing of it. Okay. Cool. And then the last one is 5 Webassign number 5b. So it says express the plane z equals x in part A was cylindrical, but part B is specifically spherical coordinates. So I think this one looks harder than it is. It actually ends up being much easier. So if you have a plane, you have x's, y's, and z's. In this case, you just have a z and an x. I think the confusing part of this one is that it looks like it's telling you like, oh, z equals x. But you should be thinking that it's just an equation involving z's and x's. So I think it might even be easier to see like z minus x equals 0 or something like that. Like this is an equation. But the point is that when you go to spherical coordinates, you know that x is equal to rho sine of theta. That's not a theta. Theta. Oh, no, cosine of theta. And sine of phi. Okay. And z equals rho cosine of phi. Okay. You also know what y is, but y doesn't come up in this equation. So you just make these substitutions in this equation. So you just get that rho cosine of phi equals rho cosine of theta sine of phi. You can cancel the rows if you want, but you could just leave it like this, and it's just plug this in. Okay. Cool. Okay. Cool. So that's this problem. Someone else is asking, while I'm on this homework, if I could look at 4b. Totally can. And then it looks like we're overdue for a break. So after this, I'll talk about, we'll take a little break. Okay. Okay, so this is a spherical shell. So a spherical shell, I think I mentioned a little bit, or had Matthew talk about it a little bit. But basically, it's just a sphere. Technically, mathematically speaking, a sphere is just the actual has no thickness, right? So it's the sphere of radius 1 is all of the points that have distance exactly equal to 1 from the origin, right? Or from a fixed point, I guess. And so it has no thickness. Usually we say the word ball to describe that same object, but with including all of the stuff inside. So, x squared plus y squared plus z squared is less than or equal to 1 or something like that. In this case, it's asking us to talk about a spherical shell, which is just a sphere with some thickness, okay? And because it's a spherical object, right? If it was in Cartesian coordinates, that might be hard. Though it wouldn't be too bad. You could, if you know equations for spheres and stuff. But in cylindrical coordinates, it just kind of becomes super easy because you get, right, remember, rho is represents the radial distance, or the radius from radius distance from the origin. And then theta and phi, if you look on a sphere, right? If you imagine you have your sphere, maybe I'll draw a picture. You have your sphere. I don't think I can draw a good enough picture. Then the angle isn't going to matter because it's still, you can be pointed in any angle and there's still a point on the sphere that represents that point. So theta and phi, you can just have them go through their usual stuff. So in this case, we can, this one will do, so this one won't do, let me make sure I'm writing visibly. So we can eliminate, just by looking at theta and phi, we can eliminate this one because it theta stops at pi. You can eliminate this one because theta stops at pi. You can eliminate this one because theta stops at pi. So just looking at the theta and the phi, right? Theta should go from 0 to 2 pi, and phi should go from 0 to pi. That's just theta and phi. That's just how we think of them, right? And then if we're looking at the radial, the distance from the origin, the origin can be 6 units up to, so if we're just looking at a cross section of the sphere, right, like at the equator or something, top down, then we have basically this is 6, and then this is 8, and rho represents this distance here, right? And so it's just get rid of that one. This one's trying to trick you into thinking maybe you have to half it or something, but no, it's just rho is exactly that distance. So it's just that one there. Cool. Someone specifically asking, why doesn't phi have to go from 0 to 2 pi? That's because, and I kind of drew this cross section earlier. Remember, phi is measuring down from the z-axis, and so it can either be pointed straight up, and then it could go all the way to straight down. And so it's just measuring this angle here. In terms of I can draw a better picture too, but basically, if you want to get around to the other side, then you just change theta. You rotate theta. So theta rotates you this way, and then phi kind of points you in the up and down direction. Okay. Cool. Cool. Yeah, so let's go ahead and take a little break. I've got 8:49. Let's call it 8:50, and then let's come back at 8:55, and we'll go through some more questions. Again, it doesn't have to be from this section. It can be from any section. But yeah, see you in 5 minutes. Okay, welcome back. Yeah, cool little break. So do we have more questions? Anything else anyone wants to talk to? Remember, we can go to we could go as far back as we want in the homework. We can also jump to, if you have an old quiz or something that maybe there's you skipped a certain problem on the quiz, because remember, the quizzes aren't you only have to turn in 2, and so maybe you skipped a certain problem and you never figured out how to do it. This would be a good chance to kind of get all that done. Yes, number 9 from 2.4. So this web assigned 2.4 number 9 we'll start with, and then you also want number 10. Okay, so let me just take a screenshot of this one. Oh. Give me 1 second. Okay. Okay, so this one was giving some people some trouble just because of how I was expecting the answer. I think people, for a fair number of people, they knew how to do it. It was just the way they expected the answer. So I sent an email about it, and I don't know if everyone saw that or an announcement about it, or one of the weekly updates I mentioned kind of this problem. And basically it's looking for the answer as x equals blank, y equals something, and z equals something. Not an ordered triple like this. So it says enter your answer as a comma separated list of equations in XYZ coordinates. So once x equals, y equals, and z equals. I don't think that this description adequately describes what it's looking for. I was confused when I first saw that, but we figured it out together. And I think I ended up giving some extra attempts for this problem. So I think you can attempt this one up to 7 times or 8 times instead of just 5. Okay, so we want to determine the equation for the tangent line to the given path at the specified value of t. So let's jump into this. If we want to compute the equation for the tangent line, we start by computing c prime. So this is 3 cosine of 3t, -3 sine of 3t, and then 7t to the 5/2. Okay. And then we compute L of t equal to, now, this is where I also mentioned in that same update, the formula I gave in lecture is a little different than the formula from the book. And so sometimes they're expecting you to use the one from the book. Typically, the formula I gave is this plus t times c prime at t. But the formula that they want is c of t equals plus t minus t sub 0 at c of t. Okay. I think this was one of the questions where they actually wanted that. And so just to highlight what the difference is, for this one, t L of 0 equals c of t naught. So in this case, t naught is this value here. And in this one, L of t naught equals c of t naught. So I think both of these are valid like equations. It's just kind of what you want for that specific application. And I think for the homework, it tends to default to this one. For word problems, it's, you can use them interchangeably. So for one of the bonus problems on the worksheet, you could use either of these. It just depended. You had to understand kind of what these meant. So basically this means this, if you're imagining that this is like a path in space that a particle is flying along, and then it shoots off in a tangent direction in a straight line at a certain point. That's how you have physical interpretation of the tangent line to a path. And so in this one, you're restarting time at that point where it shoots off. Over here, you're continuing the t parameter at the same rate. Okay, or not at the same rate. Both of these are at the same rate, but at the same point in time. So t equals 0 is still the same t equals 0 for both of these, right? So the t's mean the same thing. For this one is how you make it so that the t's mean the same thing in the original curve and here. In the equation I gave, you're like restarting time. You're restarting your new t equals 0. So t equals 0 in this case is the point where it shoots off. So I'm going to use this one here. So in this case, L of t Maybe I'll go back to white. L of t is equal to, so it's going to be a triple. So it's going to be, I guess I should figure some stuff out before I jump into these equations here. Also, this should be these should be all t0. So I need to figure out what C prime at 1 is, which is, in this case, that's my C0. So this is 3 cosine of 3, negative 3 sine of 3, and then 7. But I also am going to need C of 1. So just plugging it back into the t equals 1 back into the original. So I get sine of 3, cosine of 3, and then 2. Okay. So now if I'm using this equation here, then L of t is going to equal, the x value is going to be this x value, so sine of 3, plus t minus 1 times 3 cosine of 3. And then you have cosine of 3 plus t minus 1. I guess maybe I'll put a minus t minus 1, 3 sine of t. So that minus is just coming from the negative up here. And then 2 plus 7t. T7 times t minus 1, which you can simplify, but I won't here. Okay. And then so when you enter it as an answer, you have to enter it as, just because the way it's asking for it, x equals sine of 3 plus t minus 1 times 3 cosine of 3. Then comma y equals cosine of 3 minus t minus 1, 3 sine of 3. And comma z equals 2 plus 7 times t minus 1. That's it. So that's how you'd enter it. Okay. Oops. Okay. So that's that one. It's number 9. I had a few people email me when this one came out, which is why I ended up talking about it in that announcement, because of, I think the most difficult part for those people was, how do you enter it? It's also weird just because there's a bunch of sines and cosines and stuff, but you could just kind of leave them there and won't be too bad. So if we look at number 10 here in the same section, I pull it up here. So this is what I was saying. This is like the common way to think about tangent lines of curves, is just to think of it as some particle moving through space, and this path is describing it. And then at a certain point, it flies off in a straight line, continuing with its, velocity that it has at that point. And so the tangent line gives us kind of what happens there. And then here's where it's important that we use that other formula, the formula where the times match up, because it's now asking for, at some other time, t sub 1, what's happening here? Okay, what happens at the tangent line at this point? So we want to make sure we use this formula up here, the second formula that I gave. So that's, or the one from the textbook. Okay. So in this case, we're going to compute C prime of t, and that gives me 4t, 3t squared minus 4, and then 0. So then I'm going to need C prime at 1. So I plug in 1 for t, and I get 4, negative 1, 0. And I plug in 1 into the original equation, and I get 2, -3, 0. And then so my tangent line has the equation L of t equal to 2 plus 4t, 4 times t minus 1. I already forgot about that. I keep forgetting about it. -3 minus t minus 1. And then 0 minus plus 0 times t minus 1. That's just 0. Okay. Basically, it starts at 0 and then it has 0 velocity in the z direction, and so that doesn't change. Okay. And now specifically, since we're looking for where the particle is at time t sub 1, we're just going to plug in this t sub 1. So we're looking at this line at t equals 2, and so we get 2 plus 4 times 1 minus 3 minus 1, or 2 minus 1, and then 0 again just stays there. So the answer is 6, -4, 0. Okay, and you just enter that here. The parentheses are already there, so just notice that it does give you the parentheses already, so you don't need to type the parentheses. You shouldn't type the parentheses. Okay, cool. Any questions on that? Okay, I'm seeing that the next question is coming from the quiz. So let me just, an old quiz. So let me just pull that up. Okay. Okay. Cool, cool, cool. Okay, so now let's look at this last. So this is quiz 2, problem 2. So quiz 2. Okay, let me bring in the screenshot. Actually, this second. Okay. Okay. So we have a plane given by some equation. We have a given plane, and we're looking for the equation of a different plane, which meets this plane at a right angle. And then we want the line of intersection to hit, to be at the, for the 2 planes, right? Basically, if you have 2 planes, so let's draw some rough sketches. So we have a plane here. Let me draw it better. Okay. And this plane, it meets with some other plane. It can be hard to draw these pictures, but we'll say that. Right, so if 2 planes intersect like this, first of all, the first thing we want is that this is a right angle right here. But then we can see that their intersection is going to be some line, right? There's going to be some line of intersection here. Right here. Okay. And then there's going to be some point on that line, and that line is going to have some direction. Okay. So let's think. We're given one of these planes. We're given this plane here, and we're trying to find the other plane. Okay. And we're given information about that line of intersection. Okay. So if we're trying to find the equation for a plane, what do we need? We need 2 pieces of information to find the equation for a plane. So we need the point, a point on the plane and a normal vector. Okay. So the point on the plane is actually not going to be too hard because this line is on both of those planes. And so this point is on both of those planes. So we can just use this point as our point on the plane. The question is, how do we cook up the normal vector? Okay. So that's going to be the hard part. So first of all, this vector here is on the plane that we're looking at. So if this is, I'll label these even though it doesn't really matter. So this is the given plane, and then this is the plane that we want to find. Okay. So someone's asking if we can use the coefficients of the given plane equation. We are going to use those for something. I'll show you what we're going to use them for. Because what do these coefficients represent? So somehow this is we get the vector 2, -2, and 1 here, right? That's the coefficients. What does this represent geometrically? This is the normal vector to the given plane. So this is normal to the given plane. And since the two planes meet at a right angle, then that vector there is going along the vector, the plane that we want. So it's going something like this. Okay. Okay. Well, look at that. So this plane, this is, so 2, -2, 1 is on our, I'll say our plane for the plane that we're trying to find. And if we look at the picture, this line, this vector here, that the direction of the line is also on our plane. Is on our plane. So we're looking for the normal vector ultimately, but we have two vectors that are on our plane. If I give you two vectors and I'm trying to look for a vector that's normal to both of them, what's the computationally, what's the tool I use? Yeah, someone in the chat's already ahead of me. If I have these two vectors and I want to find a vector normal to both of them, then I just use the cross product. So I just take the cross product. So the normal vector of the plane that I want is going to be the cross product of these two vectors. Yeah. So this question, when I wrote it, I liked it, but then I also thought it might be just a little bit too hard. So I have a feeling a lot of people skipped it. So it's just, I feel like this was at the top of the difficulty for what I would accept, what I would put on a quiz. And that's why the other two are a little more reasonable, because I figured you should have at least two that you could do. But I do think some people actually still attempted this one. So then we get -4 plus, or yeah, let's see, that's minus -4. So yeah, plus 4 times I. That's cool. Plus, or I guess minus 4 plus 5j plus -8 plus 10k. Let's see. You can double check my arithmetic. There, just to make sure. The first one is, I don't remember that happening, but that's very possible. I also, just as a reminder, I do post my solutions to these, to quiz problems, or I started posting them at some point in the quarter. That doesn't mean I won't talk about, I'm happy to talk about them, because the solutions sometimes maybe leave out details, or the verbal explanation kind of gets lost in the written page. But yeah, so we get something like this here. we get this vector here. Okay. And then so if we have this normal vector and this point, so the plane we want is given by the equation 0 times x minus 1 minus 9 times y minus 1 plus 2 times z minus 1 equals 0. So this goes away and I get negative 9y plus 9 plus 2z minus 2 equals 0. I'll just clean this up a little bit to make it look a little nicer. And I get negative 7 over there. Okay, cool. You don't have to simplify it this far, but okay, cool. Any questions? I'm sure there's enough information here that you can that this plane is completely determined, but I'm sure there are other ways to approach this. That tends to happen when you do these sort of geometric problems. There's more than one way to approach it. And so so people always ask, do we have to use your method? If it doesn't explicitly say which method to use in a problem, then you can use any method as long as it's valid. Okay, because people will say like, well, I got the right answer, but just because you got the right answer doesn't mean that your method was necessarily valid. Okay, so as long as you use like some kind of valid method and don't add any extra assumptions to the problem. Okay, cool. Any other questions on this problem? I still really like this problem, but I get that it was on the harder side of the difficulty scale. So. Okay, well, we're just about out of time, so we could call it here. Again, tomorrow it's gonna be much more of the same. So, any update on the final being extended to 12 p.m. Yeah, I don't think that's gonna happen. So I'm trying really hard to make sure that the written part should only take you an hour, and so it's gonna be over 24 hours of a window, and so I'm working really hard to make sure that you have enough time. Now, the final exam, like according to the schedule, would have been 8 to 10 a.m. And so if you shouldn't have any other exams conflicting on Saturday morning. So at the very least, those 2 hours you should have free. So that's kind of what I figured. 8 to 10 a.m. on Saturday technically was the time that we had set aside for the final. So it should be clear on everyone's schedule, at least in terms of stuff for summer session. Okay, so I don't think it'll be pushed to 12 p.m. unless something drastic changes, or something very drastic gets brought to my attention, like everyone has something at that time or something. Okay. Now, individuals I can work with. So like if you have something in your life that like is just going to not allow you to have any time to work on the final, then reach out to me and we can work something out. But as a whole, it's still going to be due 10 a.m. on Saturday. Just for, again, the big part of that is for the turnaround of grades. I want to get you grades to you as quickly as possible. Okay, so if you have to go, you can go, but someone's asking about the oral exam. How will it go with a partner? You've never had an oral exam with math. That's totally understandable. This is a bit of an experiment, but also I've talked to some people who've done stuff like this before, and so I want to. It seems like it's going to be more beneficial for everyone, and so yeah, I guess I will. There's going to be a couple of questions. Part of it is just going to be you're going to work on the problem on your own, and then you can, if you're working with a partner, you can talk to each other. I haven't decided if it's going to be for both questions or just for the second question. And then we'll come together and I'll ask some follow-up questions to kind of to get it. This is also partially for you to be able to like explain your steps. It just leaves more room for partial credit also. So for example, like maybe you get the final answer wrong, but I'm going to pry you with some questions, and that's going to help me realize like, okay, this person didn't necessarily get the final answer, but they have very thorough understandings of the steps in between. They just kind of maybe misunderstood this part or something like that. And so there is going to be like the main question we're talking about, but then there's also going to be small follow-up questions about specific steps and stuff like that. Okay. Okay, no problem. Okay, so we'll call it there. I'll see you all tomorrow morning. Keep studying and bring any questions that you encounter. Okay, bring them with you tomorrow. See ya.